Thanks for tuning in to First Principles Daily, episode 31. It's July 6th, 2026, Monday, a fresh First Principles teardown to start the week. Before interchangeable parts, a musket cost many times its raw iron and wood because every component had to be hand-fitted by skilled craftsmen. In the late 18th century, a finished musket might require dozens of hours of filing and fitting after the parts left the forge. The iron stock itself was inexpensive commodity material. A single broken lock or trigger could idle the weapon for weeks while a gunsmith shaped a replacement to match the existing frame. The shift to parts made to uniform dimensions changed the arithmetic. Any lock could now drop into any stock without further cutting. The dominant cost moved from labor to the repeatable production of those dimensions. Guns had long been built the way most complex metal goods were built. One skilled worker or a small team started with rough forgings and filed, fitted, and adjusted until the pieces meshed. The convention rested on the assumption that slight variations in casting or forging were inevitable. Only handwork could compensate for them. Master armorers therefore treated each firearm as a unique assembly whose internal tolerances were discovered rather than prescribed. Under that system, the finished price reflected the cumulative hours of fitting far more than the weight of iron or the value of the walnut stock. Because every gun carried its own set of custom mating surfaces, a repair demanded the same skilled labor as the original build. The practice persisted because it worked at the scale of individual orders. The alternative of holding every part to a fixed tolerance required tools and inspection methods that did not yet exist at workable cost. Armories accepted the resulting expense and delay as the natural price of a reliable firearm. The same logic governed clockmakers, instrument makers, and early machine builders. Each trade copied the precedent of its predecessors and optimized within it. The baseline that innovators later refused was therefore not a technical limit but a social and procedural one. The belief was that precision could be achieved only after the parts were already made. A typical musket lock contained roughly a dozen interacting pieces. These included the plate, tumbler, mainspring, sear, bridle, and screws among them. Each piece had to be filed until the sear engaged the tumbler notches at the correct angle. The mainspring also had to deliver consistent force. One gunsmith might spend an entire day on a single lock. The tumbler's square hole had to be broached by hand to fit the square on the hammer stem. Any mismatch meant the hammer would bind or release too early. Barrel tangs were likewise inlet into the stock by repeated trial and error. Thin shavings of walnut were removed until the barrel lay flat without rocking. These operations added labor that scaled directly with the number of muskets produced. The labor did not scale with the quantity of metal involved. When an armory received an order for 500 weapons, the fitting hours multiplied accordingly. The supply of trained armorers became the binding constraint. Contemporary accounts describe workshops where the majority of floor space was occupied by benches for filing rather than forges or lathes. The process had organized itself around correction instead of prevention. The first principal step was to ask what physical properties a musket actually required. The question also covered what minimum set of operations could deliver those properties at the lowest total cost. The raw material floor was simply the market price of bar iron, sheet brass for the lock, and seasoned wood for the stock. These quantities together amounted to only a small fraction of the prevailing finished price. The idiot index of the conventional musket was therefore high. The dominant expense was the repeated measuring, filing, and trial assembly needed to make non-uniform parts cooperate. To see the index clearly, imagine the raw iron and wood as the magic wand cost. Everything above that floor came from the hours spent correcting each part to fit its neighbors. If those correction hours multiplied the material cost by a large factor, the index signaled that the real problem sat in the process rather than the metal. The decisive move was to invert the sequence. Instead of correcting parts after they were made, the armories invested in fixtures that forced every part to be made correct the first time. Jigs held the work in a fixed relationship to the cutting tool. The location of every hole and every contour became a property of the fixture rather than the individual workman's eye. Gauges, often hardened steel plates or plugs, replaced subjective judgment with a binary test. The part either passed through or over the gauge, or it did not. Once those gauges existed, the cost of achieving interchangeability shifted from skilled fitting labor to the one-time cost of making and maintaining the gauges themselves. Early experiments at the French arsenals under Honoré Blanc demonstrated that lock plates could be milled to a common pattern and still function. The method remained fragile until American armories at Springfield and Harper's Ferry developed a fuller set of fixtures and a division of labor. Each operation was assigned to a dedicated machine or bench. Each subsequent refinement removed another layer of hand correction. Hardened milling cutters held size longer. Drop forgings started closer to final shape. Systematic inspection occurred at every stage. The key engineering trade-off was that the fixtures and gauges had to be more precise and more durable than any single part they produced. The capital cost was front-loaded so that the marginal cost per musket could fall. Over decades, the same logic was applied to the stock, the barrel, and the small hardware. The entire weapon could be assembled from bins of parts without further fitting. Consider the lock plate alone. Under the old method, a worker would scribe the outline from a pattern. The worker would saw roughly to line, then the worker would file the edges while repeatedly offering the plate to a master lock assembly to check fit. With a milling fixture, the plate blank was clamped once. A sequence of cutters removed metal at predetermined locations. The fixture's locating pins ensured the pivot hole for the tumbler always sat at the same distance from the edge. A go, no-go gauge then verified that distance in seconds. The same approach applied to the tumbler. Its profile was generated by a form cutter guided by a cam plate. Every tumbler's notches aligned with the sear at the identical angle. The objection that forgings still varied in size was met by adding a preliminary straightening operation in a dedicated press before the part entered the fixture. The press removed the largest distortions so the milling cutters encountered consistent stock. Barrel production followed a parallel path once boring and rifling machines were fitted with steady rests and indexed carriages. These kept the bore concentric to the exterior. Each of these changes attacked a distinct source of variation rather than attempting to compensate for all variations at once. By the 1840s, the Springfield Armory could turn out muskets whose parts were sufficiently uniform that a regiment could exchange components in the field. The labor hours per weapon had dropped sharply from the earlier craft baseline. The idiot index moved downward because the expensive step of custom fitting had been engineered out of the process rather than performed after the fact. Yet the floor was never reached in a single leap. Decades were required to refine the gauges, to train inspectors, and to persuade suppliers to hold the same tolerances on forgings and castings. The remaining gap lay in the cost of the precision infrastructure itself and in the limits of the machine tools then available. Certain critical surfaces still required selective handwork. The achievement was therefore not zero labor, but a reallocation of labor from fitting to the production and maintenance of the means of precision. Even after interchangeability was declared achieved, the Armory continued to maintain a small corps of fitters for final acceptance trials. The gauges themselves could drift or wear. Suppliers of iron and brass had to be brought into the system by providing them with master gauges so their output would match the Armory's fixtures. These secondary investments explain why full interchangeability took roughly 50 years from the first French experiments to routine American production rather than appearing overnight once the idea was conceived. The cost of a musket was never set by the price of iron. It was set by the number of times a human had to decide where to file next. Once that decision was moved into the fixture and the gauge, the same iron could be turned into a working part at far lower total effort. The same transfer of judgment from the bench to the tool can be seen wherever a trade still treats each assembly as a fresh problem of alignment rather than a verification against a fixed standard. The question left open is which current manufacturing steps still rely on post-machining adjustment that a better fixture or gauge could have prevented from the start. That's a wrap on today's first principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.
I'm about to prove